Okay. Hello, those at home. Today we'll be moving on with the topic of induction current. But before we get started on induction current, I want to share with you guys this classic demonstration that's done in high school. And it's often known as the cow magnet demo. I'm not using a cow magnet because it doesn't work very well. I do have a cow magnet right over here. All right. But yeah, I'm not going to use that for this demonstration. Instead, I'm going to use a rare earth magnet. And it's a classic demonstration where a teacher will drop this through a copper pipe. Keeping in mind, guys, that copper and magnets don't stick together. In fact, copper kind of hates a magnet, all right? It slightly hates it. And if you take a look at my setup right now, you'll see that the magnet is actually much smaller than the opening. So it's freely able to move through, okay? There's no restriction due to friction. However, when I drop this through this, it's going to take longer than you would think. Because normally when I drop this, boom, it's on the ground already before you know it. But if I drop it through the copper pipe, I can take my sweet time in trying to grab this afterwards. In fact, I can just drop it from here, raise up the pipe, and just wait and wait and wait, and boom. Oh, I missed catching it. I was looking at the camera, but I'll show it to you one more time, okay? I can just drop it, just wait and wait and wait, and there it is. All right. So why the crazy, ridiculous delay? Well, that's what we're going to talk about in today's episode. All right, here I am at my desk, and let's cast the screen away. Okay, so that's the classic Lenz's law demonstration, all right, where someone would just drop a magnet through some tube that is non-ferromagnetic, and somehow it seems to slow itself down. All right, and one thing you got to keep in mind is that, yeah, there is work being done there, right? Because initially it's just falling due to the presence of gravity, but there is this force that's inhibiting it. So what exactly is that work? All right, and that's what we're going to discover in today's lesson. So there's another perspective of this video, and yeah, I'll play it right now, and if it gets copyright infringed, then I'll just delete it afterwards. But it's just doing the demonstration the other way around. So instead of dropping a magnet through a pipe, why don't we drop a pipe through a magnet and see what the outcome is?
The resistive magnet. Inside its steel casing, copper plate coils, exactly like the ones we saw Jim make, exert a magnetic field 400,000 times more powerful than the Earth's. It's a valuable tool for research, and when the boss isn't looking, it's good for party tricks too. So, just for how do they do it, they showed us a neat little bit of magnetic magic. Our glamorous assistant, Tim Murphy here, drops a chunky 2-kilogram aluminium tube into the top of the machine at 6 p.m. The intense magnetic field induces a current inside the tube, creating an opposing magnetic field. The two fight it out, slowing the tube's fall. When it finally hits the floor 12 feet below, it's 6:02. 2.5 minutes have passed. Not magic, of course, just magnets.
Okay, so yeah, the whole purpose of the cow magnet demo, it's used to prove that you can convert a mechanical work into electrical current. So that's what's really happening. As the magnet is falling through the pipe, it's creating the electrical current. And in doing so, remember that energy doesn't come free. If you want to create electricity, that effort has to come from somewhere. So what it's doing is converting that gravitational potential energy into work, and that work is then converted into electrical current, and that's what's slowing it down. All right, so the slowdown of the magnet from free fall is the conversion between gravitational mechanical energy into electrical current in the pipe. Now, if you could develop it this way, and I think a YouTuber has done that, instead of using a copper pipe, they just took a copper wire like this and just wrapped it a bajillion times around that pipe and dropped a magnet through it. And initially you won't see anything at all, but then that YouTuber, what they did was that they attached an LED at the end. And while doing that, every time they dropped it through, it would light up. Would this work? I don't know. I've never tried this. Not enough for this to work. Yeah, this ain't going to happen, is it? Yeah. All right. Their setup is, oh, it did light up just a bit like that, but I had to throw it all the way down. Okay. Oh, wait, maybe this is ruining it. Okay. Anyways, enough of that. Maybe you got to see that hint of it glow. Okay. So yeah, you can convert mechanical energy into electrical current, and that's what we're going to discuss about in this episode. All right. Now, there are two scientists that which discovered all this stuff that's happening here. The first one was Michael Faraday. All right, so Michael Faraday figured out that, yeah, you can have a changing magnetic field create current. That's what he discovered, okay? A moving magnetic field near a conductor will create a current flow in the conductor. And he was able to create a mathematical formula with it, but that was it from his research. He didn't really pay attention to which direction that the current would flow. That wasn't later discovered until about a decade later by Lenz. Oh, come on.
Let's switch it on. Let's see what it does.
Through this coil of thick wire, we're about to pass a huge alternating electric current. On top is a 1 kilogram aluminium plate.
So we hear this noise. What's that noise?
It's the vibration of the plate because it's vibrating at 2 times the frequency of this one.
Whoa! Whoa! How does it do that?
To find out, I've come to the place where it all started, the Royal Institution in London.
This is the key to Faraday's magnetic lab. It's amazing that lock still works.
From the 1870s onwards, it became a storeroom, which is why it survived, and it survived intact. All the joinery, giant electromagnet, exactly the same as Faraday.
So this is exactly as Faraday would have had.
That's right, yep.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electrical hardware shop and ask for X number of meters of insulated wire. You had to insulate the wire as you went. And so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction. He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the 2 coils repel each other when the current is induced, and that's due to the interaction of their magnetic fields. Which brings us back to this. Through the bottom coil, we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of a second coil, we're using the aluminium plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates.
How awesome is that?
This current is not only good for levitating the plate, it can also make light bulbs glow.
A gift.
Oh, thank you. Oh, that is cool.
Not too close because it will burn the arms.
Can I put it there?
Yep.
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Some water.
Thank you.
Yeah, to see the temperature.
Check out how hot this plate is. Oh, that is nuts. Is this your favorite demo?
It's like a flying barbecue or something.
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction.
Yeah, so the Cal magnet demo, it's known as Lenz's law demo. And it wasn't until Lenz came around and he discovered that, yeah, you can determine and predict the direction of current flow. Okay, so that's the difference between the two researchers. Faraday predicted that it could happen. He saw there was a mathematical correlation. That's why there's a formula with it. But Lenz was able to predict which way the current would flow. Because depending upon whether you push or pull the magnet, the outcome is completely different. And that's what we're going to demonstrate next. Yeah, you know, while people are copying down, I may as well just talk about the story about cow magnet. You know, why is this thing called a cow magnet? And it's because they do give this to cows, believe it or not. They feed it to cows. Why do they feed it? Well, I heard about the story at the CNE because where else can you hear about these crazy stories? All right, I saw this in a display one day, and I asked the farmer there. That, you know, they're having an exhibit there, and the farmer just explained it to me. He was saying that, you know, with cows, they're docile creatures. They don't really think about what they eat, so they just go out into the pastures and just chew away at anything. And as you may know, farmers, they constantly have to reinforce their fences because they're always breaking down. And every now and then, while they're walking out in the fields, they may end up dropping a nail or two into the haystack. All right, so that hay does contain some nails, and cows, they don't even think twice. They kind of just gobble their food in. All right, and as they gobble the food in, there may be a nail contained in it, and it's perfectly safe while it goes down because the hay, you know, keeps it as a safe barrier around it until they get to their stomach. But you may have heard that cows have 4 stomachs. Not really 4 stomachs, but they really have 4 separate chambers in their stomach, because later in the afternoon, they're going to go and sit outside of the pastures, and they're going to barf out their food one more time and chew away at it. It's one of the things about eating something that has a lot of fiber. You kind of have to do more further digestion with it. If you ever had a pet rabbit, you'll know that with rabbits that they eat their own poop because they need to further digest their food. Anyways, their digestive tract is slightly different than cows. Cows need to barf it out. And as they barf it out midway through, the nails have not completely dissolved in the stomach acid. So they may come their way up and there's nothing protecting anymore. It may puncture into their esophagus as they're barfing it out. And that will lead to infections and the cow may die from it. So that's why farmers, they feed cows a cow magnet. And that's what a cow magnet looks like. And we normally do most lab activities in high school using cow magnet because of its beautiful shape. It just gets the job done. Now you know, and I think that's plenty of time to move on. Okay, all right, so follow along with the animations. If we just have a magnet moving freely in space from left to right, are we doing any work? Okay, go back to the 3rd unit. Are you doing any work just by moving something in a constant velocity in the same direction? You're not getting any work done, all right? In order for work done, yes, it has to travel distance, but it also needs to put in effort. A force needs to be applied. And that's what's happening as I shove this magnet through this solenoid over here. Now, this is a special solenoid where I've attached some LEDs to it and I've wired it up. And if you're wondering why are there 2 LEDs, it's because of the nature of an LED. LEDs, they only light up if current flows in their electrical favor. If it goes opposing to their favor, they create a huge insulating barrier and no current will flow through. All right, so you'll notice that as I pull it from this end over here, did it light up? Yeah, there it goes. Okay, I don't know if you can see on camera. Maybe I need to dim down the lights. Okay, as I pull at this, you'll see that it glows red. Now, if I take this magnet and I flip it 180 degrees, the other LED will light up, showing you that the current's going the other way. And that's why you're going to see an amber color this time. So that's amber, and if I flip this around like this, you'll see the red LED. Okay, so we have a red LED and we have an amber LED, just to indicate the direction of current flow. All right, so you can see that the current flow only flows one way depending upon how I pull it and the direction of my magnetic pole. And that's what we're going to talk about right now, okay? How to predict which way the current will flow. And we'll have our assistant over here, a lovely galvanometer. All right, what exactly is a galvanometer? It's the original ammeter. In fact, in history, we started off with the galvanometer first, which is effectively an ammeter, and then it was a bit later converted into a voltmeter. They all operate under the same principle. All right, if you look carefully inside over here, you'll see that there is a little coil. There is an armature, and the armature surrounding it, there are permanent magnets. All right, so depending upon the intensity of the current going through the armature, it will rotate, either to one magnetic pole or it will rotate to the other magnetic pole, and thus causing the needle to deflect one way or the other. Simply by adding a scale on top, that's what upgrades a galvanometer into a good old ammeter. All right, so we have an ammeter that's able to predict current flow, and this measures it in, I think, milliamperes, because it's very weak, the amount of current that I generate with this. In fact, you'll notice that it is proportional to the speed that I pull the magnet with. Where's my cow magnet? Now, this magnet over here isn't as strong as my rare earth magnet, so it may not deflect. Oh, it does deflect. Okay, I'll use this as my demonstration, right? You can see that when I pull the magnet one way, the needle deflects one direction, and as I push it in, it deflects the opposite way around. And if I pull it faster, then yes, the deflection is far greater. Moreover, if I take the magnet and I flip it the other way around, now the deflection direction is completely opposite. Okay. So that's what we're going to predict out. We're going to figure out the direction of current flow, and that's what was predicted by Lenz. Henrik, I think is his first name, Henrik Lenz. Okay, so here is a magnet, and the magnet is placed inside a solenoid, and we're going to yank at it. To describe the fact that we're yanking at it, that's why we're going to write down FMECH right up here. Again, if you're wondering how would you draw that in your notes, you start off with a basic rectangle, and you can see that you got a fish hook that starts on the left-hand side. Beyond that, you have these elongated S's, which you try to visually connect them together behind. All right, so you can imagine an extension that goes up to the behind, and that's when you connect it on the other side. And that's how you neatly draw this out. And this will exit out on the back side, on the right. Okay, so that's how you'd scribble it out. And you're placing a magnet in here, magnetic south over here, and you're applying FMECH for mechanical force. And the question is, which way is the current going to flow now? Because you can clearly see that I'm generating electricity by yanking at the magnet. Okay, so to figure out what the outcome is, we have to think back to what Lenz's law has stated. And this is what you copied down in the previous slide. The direction of the induced current will create a force that opposes the motion of the magnetic field. All right, so you have to constantly think backwards when you're solving these problems over here. As you're yanking the magnet out, you are performing mechanical work. Again, if this wasn't over here, as I'm pulling it, I'm not doing any work because there's nothing grabbing it back. Okay, so as I'm pulling this, there is this force yanking it back. I won't notice it because I'm a human being and I'm just too strong for it to notice these weak forces. But if we amplify this enough, you'll be able to feel that kickback force. All right. If you've ever been to the Ontario Science Center, there's that cool ride where you pedal on it and then there's a bunch of light switches. And the more light switches you turn on, the harder you have to pedal. So that's a really good example of you being able to witness and feel that you're converting this mechanical effort into an electrical current. Okay, so you have a chance to check it out in the future. It's a pretty cool ride. And it's pretty cool to experience that the more light bulbs you turn on, the more force you have to apply to light up all the light bulbs, and the more you sweat at the end. So you are converting mechanical energy into electrical current. Okay, so this is the tabletop demonstration version. So let's just see how much current we're generating. It's going to be very weak. It's not going to be enough to light up the LEDs when I pull it that slowly. Okay, all right. So looking at the diagram up here, what we're doing is that as we're pulling it, the solenoid is fighting back, saying, hey, I don't want to see any changes in magnetic fields. In fact, I like things the way they are. In other words, this solenoid here likes it when the magnet just sits in there. It opposes any sort of change in magnetic field. So as I yank away at it, it says, no, 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 I want that thing to be back here. So it's going to fight like a bad sibling and try to hold it back. And the only way that you can logically have it hold back is if the right-hand side temporarily behaved as magnetic south, right? Because south attracts north. Now you've changed the circumstances. As I'm yanking this out, and as this is behaving as magnetic south, I just generated some current because it had to create some electricity just to create that magnetic field to fight back. And this is where you're going to apply right-hand rule number 2. So if this side of the magnet behaves as magnetic south, and I guess I have to hold the other way around for you guys. Okay, if this side here behaves as magnetic south, then I need the bottom of my hand to face there and my thumb to point in the opposite direction. All right, so my thumb will be pointing towards the left, like so. In fact, I think it makes more sense if I just use an overhead camera. That way, it's all from the same perspective. There you go. That makes a whole lot more sense. So as I yank the magnet out, again, if this is north, then this side would behave as south, and meaning I need to hold my hand like this. And as I hold my hand like this, take a look at the orientation of my fingers. All right, my fingers indicate the direction of current flow. So the current is going to flow upwards in this solenoid here. So I'm going to draw these miniature arrows called chevrons through the top of this solenoid. So what's going to happen here is that if I do hook this up to something over here, the needle will tell me which way the current will flow. And if you take a look at the setup of this, with the way how the current leaves from the right-hand side and approaches downwards, this needle will deflect towards the left. And that's exactly how you'd solve these problems.
Quick question.
Yes.
So just double checking the sum points okay, yeah, never mind. I was getting confused because when you're putting your sum over, I felt that it was going in the opposite direction of the current when you're just looking at the cylinder. But if you look at the other part, it's going in the correct direction.
Yeah. Don't associate your thumb with the arrow, okay? This is not related. There's no relation there. Okay. Instead, you need to take a look at the relation of the current, how the current is flowing through the solenoid. If you need me to repeat this again, sure, because this is our first time seeing this. Okay. So again, you're yanking a magnet. You're taking a magnet and you're physically yanking it out of the solenoid. In fact, I was able to see my needle over here deflect as I was yanking it out. All right. And that's because the true law of Lenz's law is that with regards to this universe, it doesn't like to see changes. Right, just like how inertia exists, right, where inertia opposes any sort of change in motion, magnetic fields oppose changes in motion as well, or any changes in the magnetic field. So really, you're violating the universe as you're moving the magnet through. So as you yank it out, this guy says, hey, no way, I don't want that to happen. So it's going to fight back. It's going to oppose the direction of this motion. So the only way for it to oppose that direction, to pull back so that you can convert this mechanical yank into an electrical current, is if this side behaves as an opposite pole, holding it back so that it doesn't move. I mean, at the end, I'm winning, right? So I'm winning and I am successfully generating electricity. So the magnet gets yanked out and the right-hand side of the solenoid behaves temporarily as magnetic south to try to hold it back so that you're trying to do work, right? You're trying to do work. So as it's trying to do work, it turns on, and as it turns on, it's going to generate current that's going to flow this way. So it's going to exit out on the right-hand side, enter in from the left. So if we go and connect this up to a meter, the meter will say, hey, the current is flowing this way because indeed it was flowing that way. Okay. Now draw the one on the right. This time around, just watch out. This time around, when you draw it out, you'll notice that it doesn't enter from the front, it enters from the back. So you just draw a line touching the box, and then you'll draw these backward S's, indicating that it goes this way, and it's going to exit through on the right-hand side, through the front. Again, objectively, what we're doing, I hope that's enough time for you guys to jot down this diagram over here. Objectively, we're trying to take this magnet and we're trying to yank it. We're applying something known as a mechanical force. And as we're yanking it, we're converting that yank effort into electricity. Okay, so I'm yanking the magnet out. But as I'm yanking it out, the solenoid here says, hey, wait a second, I don't want to see any changes because the direction of induced current will always create a force that opposes the motion of magnetic field. All right. And now it cannot behave as north because if it behaved as north, it's just going to fire off just like in my YouTube video. You might have seen that. I'll hook this up to a power supply. All right. So if I hook this up to a power supply, I don't know which way is positive and which way is negative. It'd be the other way around. Okay. So if I hook this up to a power supply, then yeah, the magnet will shoot out like a projectile. It'll just fly out there, okay? We don't want that because this is a case where we're applying energy to make work happen. That's back to making motors, okay? We're creating a generator. We're converting effort into electricity, okay? So that's why it cannot be a north pole. It's just going to cause it to shoot out, right? We need to abide by Lenz's law, which states that, hey, it's going to say, no, I don't want you moving, okay? I just want things to remain the same. And that's why it's going to behave as south, to try to hold back the magnet to prevent it from moving. But in doing so, it temporarily turned on the solenoid. So it's now turned on. And as it's physically turned on, you need to apply right-hand rule number 2, okay, where your thumb points magnetic north. So yeah, north is going to north is going to be on the left-hand side. And that means that when you use your fingers will have the arrows pointing upwards through the front, like so. Okay, abiding by that lovely picture there of my hand. Now that it's physically turned on, you can see that the current will exit from the left-hand side and enter in from the right-hand side, and that's why the arrow of your galvanometer will point towards the right, and that's why that's the outcome. In other words, on these questions over here, what am I testing you on? It's just going to be a picture that looks like this. Tell me which way will this arrow point? To the left, to the right, or it won't point at all. That's all it is. Okay. And if it was physically drawn, then yes, you would physically draw the arrow, telling the reader that the current will flow to the right in this case. Okay. Let's go through a few more examples. And in fact, before we move on to the examples, you might notice that between these two, they seem to be the same thing, right? The magnets look identical. So why is the outcome completely different? All right. And that's why you can't just memorize, north is the direction you should point to. That's not the case. All right. The truth is that it's based upon the way how your conductor is coiled. And that affects your answer. Okay, how the conductor is coiled. Because you can see in this case over here, the conductor starts from the front and then goes to the back. The second one, it starts from the back and then it goes out through the front and then goes around. Okay, so that's what makes these two diagrams completely different. Okay, you can see that the way how it's drawn, the arrows, they are drawn the opposite way as well. Okay, the one on the right starts from the top and the one from the left starts from the bottom. So that's what impacts it. In fact, if you need to see it visually, this is what I normally do with the students, is that I just take a piece of wire and here's the difference between it coiled around my finger here. This is version A, okay, where I start coiling it from the front. So in other words, from my finger's view, it looks like I'm coiling it clockwise to make that diagram work. In the second case, what I'm doing is I'm starting from the back and I'm coiling it like this to make the outcome. In other words, when you look at it from the camera's view like this, you can see that I'm coiling it counterclockwise to create that effect. So yes, the direction of your coiling, all right, whether you coil it clockwise or counterclockwise when you're assembling it, that will affect your outcome. That does matter. Okay, here's the third case, and the third case is the same exact solenoid as the first case, as you can see, right? They both enter in the front of the left-hand side in the coiling. All right, so go ahead, draw it out and tell me, which way will this arrow point? Will it point to the left or will it point to the right? Okay, I hope that's enough time for you to figure out this question over here. And the correct answer is the arrow is going to point towards the right. Okay, now let's explain why it's going to point to the right when you're pushing it. Again, as you force the magnet in, you're changing the magnetic fields over here because originally it had no magnet inside and it was happy with it. Again, according to Lenz's law, it states that this guy will start inducing current to prevent any sort of changes in its happy environment. It likes to stay put and not have any changes. So if I'm trying to push this thing in, it's fighting back saying, hey, I don't want to see any changes. It cannot be a south because if this was south, it'll just magically get sucked in. Okay, and that can't happen. You can imagine the crazy energy you can create from this, right? If I'm able to just put this in and just magically get sucked in, then why don't I just make a big tube that goes around a full circle and just push a magnet in there? It'll just spin faster and faster and faster, and then I become Tony Stark because I created an arc reactor. All right, I made energy out of nowhere. That can't happen, okay? So really what's happening is that as I'm pushing this in, this is fighting back, but the consequence of it fighting back is that it fights back and makes electricity to fight back. Okay, so I'm converting this mechanical effort into electrical current. And that's why temporarily on the right-hand side, it's going to behave as magnetic north to fight back saying, no, I don't want to see any changes in the magnetic fields inside of me. On the far end, it'll behave as magnetic south. And now you need to place your right-hand rule on this. But this time around, you're putting your hand behind the solenoid because it's the only way to orient north properly. Now with your hand up from behind, you can see that the current is going to go down through the front. So up through the back and down through the front. So as you trace the electrical path of the current, the galvanometer will have an arrow that will point towards the right. Jot out the last one and work it out. Have you made your predictions on the fourth one? Which way did you predict? Hopefully you got that answer. Okay. And now let's try to solve and figure out why does the arrow point towards the right. Okay. Again, we're trying to shove a magnet physically into a solenoid. Okay. And as we're physically trying to push it in, the solenoid will fight back according to Lenz's law, which states that, hey, it doesn't want to see any changes in its magnetic field. It's happy having no magnetic field. But it'll just temporarily turn itself on. And as it turns itself on, it's going to behave as magnetic south over here to prevent the magnet from going in. Of course, in trying to prevent it moving in, it ends up creating electricity. Where north is on the left-hand side, south is on the right-hand side, and you need to place your hand in front of the solenoid. Oh, my hand's not animated? Aw, I don't have a hand animated here. That's too bad. But you can imagine my hand being placed in front over here, like so, to make the diagram work in our favor. Okay, so with my hand over here, we can see that the current is all pointing upwards on the solenoid. And as you trace the path of the current, it's going to result in an arrow pointing towards the left. Can't you solve that without the F mech? Well, without the F mechanical, how would you know if this is going to be south or north? You wouldn't know. In fact, if you look at the first two diagrams, The difference between these two is that one is pulling and the other one's pushing. As a memory aid, if this helps out, there you go. When you pull, expect opposite pulls. When you push, expect the same pulls. Maybe that'll help out for some people. Okay, so just to share with you one more time the outcomes of this setup over here. Again, I have a galvanometer here, and this galvanometer, if I actually knew which way it would point properly, I could predict it out, but I just know that the outcome will be different. If I push it, or sorry, if I pull it because it's already here, you'll see the needle deflects that way. And if I push it, the needle deflects the opposite way. Okay, pull, it goes one way, I push, it goes the opposite way. And if I take the same magnet and I flip it around 180 degrees, now I have the south pole, so the deflections will be in the exact opposite way. Now when I push it, it's going to go to the left, and when I pull it, it goes to the right. Right? You'll see that this version over here, they're going in the same orientation. Meanwhile, when we take the magnet and flip the other way around, then the orientation of the current flow is opposite of each other. So yes, the direction of your magnet makes a difference. Whether you push or pull, it makes a difference. And lastly, how you coil it. Now, with the ones that we purchased over here, they're all coiled in the same way, which looks like counterclockwise when I hold it this way. All right. I don't have any purchased ones that are coiled the opposite way. I think they're all manufactured the same way. Yeah, they're all manufactured in the same direction. So I can't show you by replacing it, seeing that the coil direction change will change the outcome. Okay, well, the magnetic power change, again, as I said, the power will change based upon a few things, all right? First off, yeah, the quality of the solenoid, what you use as your core for this. This is an air core, so it's going to do a terrible job. And yeah, the permanent magnet you use, because with a weak magnet, you can see that it only deflects a little bit. Meanwhile, with my rare earth magnet, where if I placed it right over here, I avoid using this because when I push it in, oh, it's working this time. Normally it gets stuck. All right, because it deflects it so heavily because it's such a strong magnet. You can see that, you know, it's pushing and pulling so strongly, even though I'm not moving it very quickly. And this one, I can push and pull it very quickly, and you can see I'm not generating much at all because this is a much weaker magnet. Okay, so there are many other factors that can influence it, but we're not concerned about that in grade 11. Grade 11, you just need to make sure that your arrows are correct. As for the numbers and intensities, that's safe for grade 12 when we deal with the math for this. Okay, so when you're generating electricity, okay, you'll notice that in generating electricity, you have to have this change in current nonstop. It's the only way to generate electricity. Often in times, they end up using an AC generator at, for example, hydroelectric plants. So they have built-in slip ring commutators. And with a slip ring commutator, it automatically causes the current to flip forwards and backwards as you rotate it around. All right, so do you need to copy this down? No, you don't. The only thing that I really want to point out is that if you look at the center of this motor, you'll notice that I have two separate rings. And that's how you can identify this as an AC motor. Okay, so that's the important thing over here. And as the armature moves and rotates around, you'll see that it's pulling away from north. So as it pulls away from north, it's going to temporarily behave as magnetic south to avoid changes in motion. And as it crosses towards the south, it's going to behave as magnetic south to oppose changes in motion. All right, I'm still looking at this side of the armature. As I yank it away, it's going to temporarily behave as magnetic north to prevent any changes. And as it's moving towards north, it's going to fight back and say, hey, I don't want to be near north, so I'm going to behave as north. So you can see that there's always this alternating change between north and south as you rotate it around. And that's what generates this whole left to right to left to right over and over again, or alternating currents. Okay, so that's how generators are created. Now that's that of an AC generator. I do have a DC generator here as well. And that's really easy to make. If you guys have hobby toy motors, you can make your own generator. All you need is a motor and maybe something to identify the direction of current. Okay, and that's what I have right over here. So here's an ordinary motor, right? With an ordinary motor, if I apply a DC current into here, the armature will start spinning. That's what I have over here, just to prove to students that it'll spin. But I think you've already seen motors already in action, so I'm not going to energize this one. Instead, what I want to share with you is this one over here. It's the same exact motor, but I'm pushing it in reverse. So really, any motor that you spin its armature will generate electricity. And you'll notice that the LED on the left is lit up as I turn it, well, at least clockwise from my perspective here. But if I turn it counterclockwise, the opposite LED lights up. All right, so the direction of my turn over here will impact the direction of current flow. So there you go. As I turn clockwise, the current flows that way. That lights up this LED. And as I turn it counterclockwise, it lights up the opposing LED. And if I do them both at once, then yeah, I got a police light right over here. Okay, and if I do it fast enough, it'll look like both of these LEDs are lit up at once. All right, and that's an outcome you might see in a future demonstration in today's lesson. That's why I wanted to point that out. Okay, so here comes the next part of today's lesson, which are transformers. What exactly is a transformer? And no, I'm not talking about these guys over here, okay? It's not a robot in disguise. Instead, it's another electrical appliance, all right? And you've probably seen them before. Maybe you've never seen them that small because that diagram over there is a tiny little thing that'll fit in my hands. And instead, you've probably seen either transformers on top of poles or you've seen transformers in your front lawn. Okay, so transformers come in many different sizes. Here I have one which is about the size of the tip of my index finger. This one is the size of my thumb. All right, and the ones that you've seen there, like for example, the middle one, it's a little bit bigger than a trash can. It's probably the size of an industrial trash can. And the green box in front, I'm sure if you're a kid, you could play house in it if they cut a hole open, okay, because it's pretty big. So all three of these, they are transformers. And why are they called transformers? Well, their whole entire purpose in life is to transform. Not to turn into robots, but to transform electricity. Okay, remember that electricity can be described using two parts, right? The power that's delivered is based upon current times voltage. And you can have the same exact power value by having different values of current and voltage. For example, you can have a very high current and a very low voltage be equal to a very low current and a very high voltage. Here's a mathematical example, all right? Let's say that we have power that's being delivered at 10 watts, which means 10 joules per second. All right, and that 10 joules per second can be delivered with either a high current and a very low voltage, like 10 amperes times 1 volt, or it could be transferred by 5 amperes multiplied by how many volts?
2.
Good, 2 volts. All right, or it could be delivered by 2 amperes times 5 volts, and so on and so forth. And that's all transformers do. They just simply transform from one state to the next, abiding by the conservation of energy. Energy cannot be created or destroyed. So they're just converting energy into a different form, either into high current or into high voltage, meanwhile maintaining the same power. That's all transformers do. All right. Now, if you accidentally buy the wrong type of transformer, let's say you buy a step-up transformer by accident, it's not the end of the world. If you want a step-down transformer, you take it and you rotate it 180 degrees, and now you have a step-down transformer. Okay. Now, the name for the step-up and step-down implies on how it treats the voltage. If it forces the voltage to go up, it's called a step-up transformer. If it forces the voltage to drop down on the other side, then it's a step-down transformer. In any case, you got to keep in mind that both of these will abide by the conservation of energy. So voltage goes up, current has to go down. If voltage goes down, then the current will go up. All right, that will always be the consequence of it. Now, we're dealing with the most ideal cases in today's homework. But as we know in reality, some of the power is wasted away as heat. This green box over here, even in the coldest of winters, you'll always notice that it remains a green box, doesn't it? All right, you can look outside in the winter in the future, and you'll notice it's always a green box, and it's because it does dissipate off a bit of heat, and in so, it ends up melting some of the snow above it and around it. So that's why it's always visible in the wintertime. Okay, so this is a consequential reality, but for our calculations, we're going to assume an ideal environment. So we're not going to deal with any sort of power losses in transformers. Okay, see all the hands are down, and that gave me just enough time to grab all of my next demo equipment. Because how do you make a transformer? It's not that hard. A transformer, all you need are 2 solenoids. That's all you need, right? 2 solenoids, preferably of different coilings. Because what scientists have noticed is that if you make more coilings on the secondary coil, the voltage will go up. All right, so you can imagine if I had one of these chopped down like this. Okay, so I had more coilings on the secondary one. So we always order it this way. So the initial coil that the power is coming in from it's from the left-hand side. It's kind of like reading a sentence. We read sentences from left to right. Okay, so that's why often in schematics, you'll also notice that power supplies are drawn from the left and the loads on the right-hand side because they're just reading it this way. Okay, so the left-hand side of the transformer is called the primary side, and the right-hand side is called the secondary side. All right, and scientists have noticed that if you had less coils on the left-hand side and more coils on the right-hand side, the voltage will spike up. On the other hand, if you flip it the other way around and you had more coils in the beginning and less coils at the end, the voltage will drop down. All right. So how does this create the magic? And let's talk about that. Okay. How does it transform energy? All right. For one thing, transformers, you'll notice that they only work for a brief moment in time under a DC power supply. Okay. So what's happening is that, let's say that we had a DC example. So I had this plugged into a power supply. I'm not going to do it in real life right now, but let's say it's plugged into a power supply and it's constant DC current. Well, yeah, that means that this solenoid will turn on, and the moment it turns on, it behaves exactly like that of a magnet. And if it's in close vicinity to the second solenoid, then it's like a first magnet being pushed into the second magnet. But again, if the magnet just stays there, you've only created electricity in the process of changing the magnetic field. Once the magnetic field is stabilized, nothing happens. So with regards to transformers, what you need to do is you need to quickly turn it on to energize the second coil, and then you need to quickly turn this off to simulate as if a magnet is being pulled away. All right, and as it's being pulled away, it creates current on this coil here. Moreover, what you can do is that you can make this guy have current that goes this way, turns off, have current go the opposite way, turn off, go this way, turn off, go that way, turn off, and just keep on going back and forth. And as you alternate your current, the second one has to respond, and it has to generate electricity as well. Okay, so here's a pictorial diagram of a transformer. As I said, transformers are always built up with two separate solenoids. And to improve the efficiency of the solenoid, they often have an iron core. The iron core allows you to deliver the B fields properly into the solenoid. All right, so without the iron core, it'll still work. It just won't work as efficiently. Okay, so if you want it to work really well, you have to put an iron core in. And that's why, with regards to the old school transformer blocks, they are heavy. Like, for example, my power supply over here, I'm not going to drop it because I have a glass table. Oh, boy, that was kind of stupid of me. All right, but it is crazy heavy, and I'm glad it didn't shatter, as this is tempered glass. Okay, so yeah, real transformers are brutally heavy because there's an iron core to help it work efficiently. Okay. So I do need to have an iron core to make it work well. I could live without it, but then it'll be super light and it won't work as well. Okay. And as I said, what happens here is that you deliver the current into the first coil. The first coil creates its own B fields. The core allows the B fields to properly be transferred into the second solenoid. And as it's being transferred into the second solenoid, it fights back and says, hey, I don't want any changes in magnetic fields, and it'll temporarily generate current to fight back at it. Again, if you remain at DC, it'll work for a brief second, and then it'll stop. Nothing will happen. You'll need to have AC current, so you're simulating as if you're putting a bar magnet in, and then yanking the bar magnet out, then putting the bar magnet in, and then yanking out again. So you're constantly having varying B fields in the second solenoid. And there's a lot of technology that operates under this principle. All right. For example, my electric toothbrush. Okay. I don't have it here with me right now, but you've probably seen these bases in your washroom. This is the base to use to charge your toothbrush. And this is the more modern version of it, because the old ones, they had little electrical probes that stuck out. But unfortunately, with regards to electricity and water, they don't mix very well. And even worse, they don't mix with toothpaste, because the toothpaste and the water will eventually corrode and erode away at the contacts. So that's why with modern day electric toothbrush chargers, you will not see any sort of metal contact. It's just insulated by plastic. If I was to crack this apart, what I would see inside is a solenoid. So I do have AC current traveling inside over here, and it's AC current somewhere in the kilohertz range. I can measure it out in the future. I just haven't measured out lately, so I don't know what it is specifically. Okay, so if I end up placing another solenoid inside the solenoid over here, I effectively have a transformer. And that's what I did one day with regards to this lonely LED. All right, I borrowed it from Mr. Patterson, if you know where he is, and yeah, I've been borrowing for 10 years now. All right, and I specifically wanted one to be green, and it's because I wanted to have a green ring of my own, if you know where that reference is from. So after you say that whole chant, this should light up. Now, if you look carefully at the setup over here, it's nothing more than an LED and just a bunch of wire coiled around. Effectively, this is a short circuit. Okay, there are no batteries here. But it is a solenoid. So as long as I have a changing magnetic field of this magnet going in and out fast enough, this LED will light up. Now, no matter how fast I try with this, it's not going to work. And that's why I'm just going to rely upon this. All right, cue the imaginary music. And as I drop this down, watch the magic as it happens. Booyah. There is my lovely magic lantern ring. Okay, and as you can see, there's absolutely no electrical contact between the two, right? They're just floating in space, but it still lights up. One cool demo just to show on the side is that, yes, this is set up in such a way that the north and south pole are always constantly like this. So north is here, then north is there, then north is here, and it keeps on jumping back and forth. And this has to be aligned in the same dimension as it for it to light up. Because if I decide to rotate this at 90 degrees, nothing's going to happen, all right? Because they're orthogonal to each other. They have to be in the same magnetic dimension in order to induce the current. And that's why with transformers, they need to use that iron core to be able to realign the magnetic fields so they're properly traveling through the second solenoid. And there's the magic for that. Okay, so what have we learned so far? Transformers only function if there's a change in magnetic field strength. If there's no change in magnetic field strength, the transformer is useless. Okay, and that's why we have to use AC current. Luckily for me, I can generate AC current right over here. All right, I do have a power supply that can generate AC current. So I just have to simply probe this into the AC line. Let me just remove my permanent magnet because it's in the way. I'll plug in my, whoa, I was about to fry out my setup. That's the one with the LED on it. Okay, I don't want to fry that one. I want the one that's free of the LED. Okay. In fact, yeah, just to show you some cute little magic, why not? Because I already have it set up. Here is my magnet, okay? And with this magnet over here, depending upon the direction of current flow, it'll either suck in or spit out under DC current. I don't know how it's set up yet right now because I haven't done all the finger measurements. In fact, we probably could do this right now. Why not? Why not? Okay, let's abide by the arrow over here, which is when I place this in here, the current will flow upwards, which it will with the red. And I better switch this over to DC so it'll work out. So according to this side will be magnetic north and this side will be magnetic south. And I'm pretty sure I set it up that this side will be north. So in the setup over here, the moment I tap it down, the magnet should get sucked into the solenoid. Let's see if that theory is true. What? Okay. I wired it wrong. Sorry. Here we go. It should get sucked in. Do you see that? It got sucked in. Meaning that if I reverse the polarity of the current, the magnet should get spat out. And there it goes, okay? Again, this violates what we talked about with regards to the first part with Lenz's law. Because remember, with Lenz's law, we're not applying electricity into the solenoid. Okay, here I am just to show you that, yeah, I could create this push and pull, and that's how we can convert electricity into mechanical motion, right? Now I'm going to replace this with the second solenoid, and I'm also going to convert this from AC current into DC current. All right, so I have it wired up as DC current. And ready to see the magic, guys? Here we go. Oh, wait. Let me turn this off. Let me dim the lights just so that you can see it better. Okay. And here comes the magic. Ready? 3, 2, 1. Ta-da. Ta-da. Oh, no. Dun. Oh, no. Dun. Oh, no. Oh, no. Oh, no. I wish I had my keyboard ready so I could play those two measly notes. Anyways, you get the idea. This isn't working right now. Why is it not working? Let me just turn off the power supply. It is working. The power supply is working. Normally, I would ask a student to come up to the classroom, and I'd ask them to feel what's going on as you place the magnet inside, and they'll feel this vibration because this is constantly moving in and out at 60 hertz, and they'll feel it. Okay, the magnet will just be jostling back and forth like crazy. Okay, I think I can somewhat demonstrate it by placing this nearby. There you go. So you can hear it. Okay, so it's just jostling back and forth while it's inside the solenoid. So why isn't this working so well? And the reason why it isn't working so well, it's because I'm using the worst solenoid ever, right? The worst transformer. It's an air core. If I want this to work better, I should not be using an air core. Instead, I should be using an iron core, all right? So I have two metals over here. One of them is aluminum and the other one's iron. One way you can tell the difference between the two is that, for one thing, aluminum's a lot lighter and iron's a lot heavier, okay? And another way of doing it is just by using a pen and tapping away at it. All right. Iron tends to be a lot more brittle than the aluminum, so the aluminum will be a very damp sound, and the iron one will resonate. Whoops. I'm not holding it right, but if I hold it in the right spot, you'll hear that it does resonate versus the very flat aluminum. Okay, so this one's aluminum, and you can't use aluminum because if you look at aluminum, no magic happens. If I really want the magic, let's cue the Oh, wait, it's not even on. That's why. Okay, but just to prove to you that it's on right now, aluminum won't do anything because aluminum is not ferromagnetic. All right. This guy over here is, you can see that it's attracted to my magnet over here. Okay. So it is ferromagnetic. So when I place it in, you'll see the magic happen. And yeah, let's cue up the music because it's worth it. What you know about rolling down in the deep when your brain goes numb? You can call that mental freeze. When these people talk too much, put that stuff in slow motion, yeah. In slow motion, yeah. There you have it, physics at work. And if you look carefully, you'll see that the red LED and the amber LED are lit up at once. And it's because the current is constantly changing. In fact, let me change this demonstration around and just to show you the consequences of DC current. All right, because with DC current, the moment I tap this down, in fact, I'll have it set up this way so that you can see me tapping it. The moment I tap it, this will build up a magnetic field. It'll be induced by the second coil. It'll temporarily turn on either the red or the amber LED. But once it reaches its magnetic saturation, nothing else will happen. It just the lights just disappears. The only way for me to continuously generate current is if I pull this away, thus collapsing the magnetic field over here, causing a change in magnetic field over here, and you'll see the opposite LED light up. Here we go. Whoa! What was that? Oh, that was on me. Oh, okay. What happens when I connected this together? The rod became attracted to the box and it created that big bang. Oh boy. All right. So there you go. See, I plug it in, it lights up temporarily, and that's it. And when I unplug it, now the opposite light lights up. I just want to decrease the voltage because I think it's just too much for this right now. But see, on just then, off then. All right. So I have to have this continuous change in current, and that's the only way that I can induce current into the second coil. Okay. All right. So that's how all transformers work, all under that principle. Wow, that was a scare. Okay. So here's the mathematical formula for a transformer. Okay. VP over VS is inversely proportionate to IS over IP. That is true. And I'll derive it for you momentarily. Also, as I mentioned, scientists have noticed that the voltage is dependent upon the number of turns. As you increase the number of turns on the secondary coil, the voltage will increase. All right. As you decrease the number of turns on the secondary coil, the voltage will drop down. So they are directly proportionate. Current, on the other hand, they are inversely proportionate. Okay, so let me just prove the left-hand side of the formula because that's fairly straightforward. Okay. Where we know that the primary in, the power in, also the power of the primary, is equal to the power out, known as the power of the secondary. We know that P is equal to IV, all right? So IV of P is equal to IV of S. So if we divide both sides by VS, where these two divide each other out, you end up getting, well, what you see currently, all right? And I'll also divide both sides by IP. That way, these two cancel out. And once that's done, our final formula will be VP over VS is equal to IS over IP. So that's the formal proof to prove this side over here. So this will be the last slide. So if you don't get it jotted down in time, don't worry. It's just going to remain like this until the end. Okay. So we see that, yeah, we have to have AC current. That's the reality of it all. So our voltage in, or a voltage of a primary, is equal to 120 volts AC. You could write down VAC if you want to, but you can also leave it as V, and I'm totally fine with that. Okay. So here are your givens. VP is equal to 120 volts. It also draws 10 milliamperes of current. All right. So the current that's going into the primary coil is equal to 0.010 amperes. Now, as for the number of turns in the primary coil is equal to 300. All right. And if you're wondering, is there a unit with it? No, you're just physically turning it around 300 times. In fact, I have another transformer over here that a student donated to me, and it's pretty cool because transformers come in many different shapes and sizes. All right. So here's another example of a transformer. All right. And it's just wire that's coiled inside with another wire that's coiled around it as well. Okay. So yeah, it just has physically 300 turns on the primary coil, and it has physically 30 turns on its secondary coil. All right. And this question over here is asking, well, what is the output at the end? Okay. So as for the schematic, if you want a schematic on the side, there's the primary coil. I know that's not the best of coils. And here's the secondary coil. Now, if you want to draw everything closer to scale, you're not going to draw all of 300, but you'll just draw significantly more on the left-hand side than the number of turns on the secondary side. Okay. So in this setup over here, we have a VP of 120 volts in, and we have an IP of 0.010 amperes going in. And what do we know about our outputs? Well, we don't know our VS yet, and we don't know our IS yet either. We're going to go and solve both of them. And the hint in solving it relies upon these two ratios here. Okay. So we'll start off with the first one. Now, this formula up here, you kind of treat it just like, you know, the sine law in math class, right? You don't have to deal with all equalities at once. You can either deal with the ones on the left, or you can deal with the ones on the right. Oh, I erased everything. Or you could do with the two extremes, all right, to get to your answer. I think I have, yeah, at least that's typed out, so that makes my life easier. Okay. And then, yeah, I just have to redraw the diagram again, if you want the diagram. Now, you can also draw these two vertical lines, and the two vertical lines tell the reader that you're using an iron core, which just tells the reader that it's more efficient than an air core. As I've shown you, by using an air core, it just doesn't work as well. It'll work, but not as efficiently. Okay, and that's why transformers are crazy heavy. That's a consequence of its design. Okay, so if you ever used an old transformer before, like the brick ones that you plug in the wall, that's why they're so crazy heavy. Okay, so you have your VP, IP, and you have your VS and your IS on the secondary side. Okay, so I'm going to start off by finding out the voltage first. So I'm going to equate these two extremes first. Okay, so VP over VS is equal to NP over NS. So if I'm trying to solve for the voltage of the secondary, that's equal to the voltage primary times NS over NP. So just make sure you're comfortable with rearranging these equations. Some of us can do this already in our heads. That's right. P is for primary, S is for secondary. There you go. Doing something like that helps in your notes, then by all means, go ahead and write the whole word out and highlight away as necessary. Okay, so this is equal to 120 volts. Again, you can write down AC if you want to, but it's not necessary. 120 by your NS, which is 30 over 300. In fact, before I move onwards with it, look at the setup over here. We had more turns at the beginning, and we have less turns at the end. So this is classified as a step down transformer. So we expect the voltage to go downwards. All right. And if it goes upwards, you know you made a mathematical mistake somewhere. All right. So in this case over here, a 30 to 300 ratio is down to a tenth. So 120 volts drops down to a safe 12 volts, which many electronic devices operate under that. All right. Now, most of the electronic devices, they don't rely upon voltage. Instead, they need current for things to drive. Again, motors only work because of current. If you remember right-hand rule number 3, motor principle only works because of I, not because of V. Okay, so most devices out there work because of current. So you want to drop the voltage down, but you want to increase the current so that it's usable. So let's do that calculation now. Now, to avoid recycling numbers, I'm not going to use the VP-VS pair. I'm just going to reuse the NP-NS pair. All right, so IS over IP is equal to NP over NS. So IS is equal to IP times NP over NS. So the current started off at 0.010 amperes. You could also write it down as milliamperes. There's nothing wrong with that. Okay, and it won't impact your answer at the end. And the reason for that is that you're multiplying by a ratio, right? You're multiplying by a 300 to 30 ratio. So if you start off in amperes, your final answer will still be in amperes, 0.1 amperes. And if you start off in milliamperes, then yeah, you will have an answer in milliamperes as well, where this is also equal to 100 milliamperes. It doesn't matter to me which one you state. They're both correct. All right, so you can see that the voltage went down. So the voltage has decreased, but the current has increased. That always happens with a step-down transformer. Any other questions, guys? All right. With that, your homework tonight is course pack page 59. So your homework is CP 59, all of it.